Thank you for joining the Fire Suppression Systems Association webinar on Protection of Energy Storage Systems. Your phone lines have been muted. If you have any questions during the presentation, please type them in the question box on the bottom right-hand side of your webinar control box, and we will take them throughout the presentation. This webinar is being recorded and will be available to download next week. With us today, we have our webinar chair, Todd Stevens with Canistraro, and our presenter, Paul Hayes with American Fire Technologies. I'll now turn the mic over to Todd to introduce our presenter.
Thank you, Becca, and welcome everybody. Before we get going on the webinar, I have two quick announcements. We often get questions of how do we get more involved in the FSSA? And one way would be to sponsor these webinars that we're showing today. So currently, we're seeking members and non-member companies with interest in sponsoring these webinars. The cost is $750 per webinar, and it involves all your company's information on all the webinar communication. That includes the e-blast for advertisements and also on the website. We'll also include a single slide regarding your company's information that will be shown during the webinar, and I will do a introduction to your company as the sponsor. So that's one way to get involved. A second way is through our marketing e-blast sponsorships. What the FSSA currently does is send out an email once a week to over 8,000 contacts within our industry. The e-blast that we send out consists of information of our association, our industry, and other popular fire suppression topics. As a sponsor, you can get your company information, website, email, and contact information of someone at your company included in each one of those emails that go out. The cost is $100 per week with a commitment of at least 4 weeks. So if your company is interested in getting more involved in FSSA and getting your name out to our membership, please contact Becca. Her information is in the bottom right of the slide that you can see right now. You can email her at becca@fssa.net, and she can send you some more information on both sponsorship opportunities. So with that, I want to move along to our webinar. Today is a really hot topic. It's the protection of energy storage systems. Our presenter is Mr. Paul Hayes, who's a general manager at American Fire Technologies. Paul is a graduate of NC State with a BS in civil engineering. He's a professional engineer in civil and fire protection in over 35 states. Paul has 30 plus years experience in managing special hazard fire protection companies, primarily in the industrial and power markets. His more recent focus has been on the leading edge design and development of detection and suppression systems for lithium-ion battery facilities. He's a member of numerous associations and currently is on the board of directors for the FSSA. Paul did an abbreviated version of this presentation at our annual forum back in February. We got a lot of great feedback, and I'm happy to have him here with us today to expand on that conversation and speak to you today. So with that said, I'll hand it over to Paul.
All right, thank you very much, Todd. I hope everybody can hear me well. I appreciate everybody's time today. I know it's kind of a weird and wonky world right now, so thank you for taking your time out of your day to call in and listen. We are going to take questions through chat. I will try to address those as I can throughout the meeting, but some of them, depending upon how far in the weeds we get, we may defer into the end. One of the things I always start off with in our world is unintended consequences, and I find this slide to be very representative of what we deal with in the fire industry. Somebody needed power, they put a junction box out there, apparently it caught fire, so they decided to put a fire suppression system in by adding an extinguisher out there. And sometimes that's a lot of what we have to deal with in the world out there, is that we come in and behind to try to figure out what somebody else has already done. So energy storage systems are developing very quickly in the marketplace. There's a lot of products. There's a lot of companies that have jumped into this. And We've seen a lot of lessons learned in the last year, the developing codes and standards trying to protect us. That's not to say that there's still not a lot to learn in this world. So what I'm going to talk to you guys about a little bit is the thermal runaway, a little bit on Arizona and what happened in that system, some off gases to failure, a little bit on the hazards, some suppression, mitigation measures, and some takeaways. One of the things that I always look at to help us is defining a fire event as an assessment based on a reasonably anticipated event to control the fire until an informed party can determine the next step of action. Now, a reasonably anticipated event can be severe, something as an explosion, but it is anticipated. We need to take it into account. So it's not minimizing, but just understanding what the risks are. So batteries 101, this is actually a single cell. It is a pouch cell. It probably measures about 12 by 12 and less than about a quarter of an inch thick. So it's not really very big. So what we see is these get put into a rack. So in modules, this particular rack probably has over 1,200 batteries in it. Now this is something that'll keep everybody awake. See if you're paying attention today. This is a single cell inside a standard junction box. There's nothing special about that. It is purely a metal container that was allowed to build up a little pressure. The battery was driven hard to failure, and that is one cell going into thermal runaway and exploding and burning. So you can see it's a very energetic fire. So where do I get my information from? I've had the good fortune of being involved with a lot of different people in the industry. I've seen some practical knowledge out there. I've had the opportunity to be involved in some research and some fire tests. We have this little term that we call brown paper bags. It's this concept of, I really can't share this with you, but here's some information that might be useful for you. So it's kind of a, buddy, have I got this for you? And I've had the good fortune of seeing some of that information that I can't tell you where I got it from or where I learned, but it's valuable information that I believe is appropriate to our industry in sharing best practices. So we look at what products are in the market and how do we make things work. Probably one of the most important concepts here is to understand really what we're dealing with from a fire standpoint. You know, electrical fire is considered a Class C. An electrolyte fire, that's actually the components inside the battery, is a Class B fire. And then there's this concept of thermal runaway, which really doesn't fall under either. But we want to take into account life safety, first responders. Are we taking care of assets? Are we taking care of life safety? What are we looking at when it comes to detection and suppression systems? And this concept of, you know, a lot of the electrical work we deal with, you flip the switch and it's dead. With batteries, that's not the case. We have what's referred to as stranded energy. So you can flip the switch, turn the whole system off, but we've got the same amount of energy that still exists inside that enclosure. And especially in a fire condition, that energy doesn't go away. So what we look at from thermal runaway is it's not an electrical hazard. It's not a fire condition. It is a thermal management issues that can lead to a fire condition. So right now, there's no technology once a battery has started moving into thermal runaway. It's basically shorting out internal to the battery. You can't stop it. So what I want to define is thermal runaway is internal to a battery. Propagation is what we call external. That's different than fire propagation, but it is propagation of heat transfer between cells to modules, between modules to racks, etc. And keep in mind, this is still a very low probability event, but unfortunately, the outcome can be very catastrophic in the consequences of failure modes. And that leads us kind of into one of the things that we saw and probably a bellwether event in the industry. And let me clarify for everybody, I know enough about this event, but I am not authorized to speak for any individual. This is some information that I have gotten from the industry, and it is my own personal opinion. Some of this is, you know, facts on what was there, but the consequences and the outcome are really my evaluation. So it was a dedicated use building. It was set up to Section 608 in the IFC. It's not a particularly big system at 2 megawatts. It is NMC batteries, which tend to be more energetic than most of the other products in the marketplace. And it was installed in 2017. So as you can see, it's a walk-in unit. There were 8 HVAC units. Smoke detection did go active. They did dump the Novak system. There was no sprinkler. There was no explosion control or deflagration protection, and there was no exhaust. So when they got there to the site, there was seen some venting, some white smoke hugging the ground, consistent. Whether that was actually fire or not quite clear. The responders were patient. They were in full PPE. They were out there for approximately 4 hours. They opened the door. They continued to monitor for explosions and toxics. There was an explosion. It removed both doors. And as you can see here, it blew the one firefighter 75 feet from that door. He actually had to go underneath the fence in order to get to that point. He is out of the hospital now, but he's probably going to be facing damages and recovering for the rest of his life. So you can see a little bit of what it did to the building. It deformed it pretty extensively, blew the door off. Most of the panels you can see on the HVAC system blew out. So any place that it could release that pressure, it took that pathway. So there's approximately 24 units, and units can be interchanged with the term rack, cabinet, whatever you want to call it. Probably modules, each containing somewhere around 22 to 24 batteries. So there was probably 300 plus modules. We think that only 2 modules propagated or 1 rack. Novak did extinguish the flame, but the gas continued to release. And thermal runaway continued, propagation continued. We believe that infiltration of air created an explosive environment. Now keep in mind, this is only one container at 2 megawatts. There are more than, I've got 1 gigawatt on here, but I know of a project in and of itself that's going to be 2 gigawatts. So the amount of energy that's going to be coming down the road in this type of environment is huge. Even as early as about a month and a half ago, there was some fairly significant articles of town boards implementing moratoriums, and this particular article on Bloomberg was a reference back almost 9 months ago to the Arizona fire. So it is still in the news. It is still making news. It is still political in nature. So part of what you're dealing with out there is the fear in the world on of the concerns, the fear, however you want to phrase that, of people not necessarily understanding batteries. So one of the things we look at is where's the initial failure mode? While the batteries take the brunt of the hit, it's actually out. Sourced items, overcharge, overheat, environmental conditions, physical damage that really cause the batteries to be pushed into failure mode. So before they go into thermal runaway, a distressed battery will release a very small amount of gas, less than a second, less than a liter of gas. Now pay very close attention to this video, because if you blink, you're going to miss it. All right, I'm assuming it's going to run. There we go. So that was an off-gas event. That was pushing it to failure mode. That is not thermal runaway, but that is a release in pressure. So what do we see when we get into an off-gas event? There's a variety of components, and keep in mind this is a kind of a generic summary, because any one of these percentages can be up or down depending upon the composition of the battery, the type of battery, the energy levels, etc. So these are just a relative number to give you an idea. So in an off-gas event, we see about 50% hydrogen, about 15% hydrocarbons. And that little bitty puff may also have to be picked up in a high airflow event, because you're moving a lot of air through these containers. Now, if we get into a battery that's failed but not burning, this is a relative composition that we see. A little less hydrogen, a little less hydrocarbons, a little more CO and CO2. But the problem with that failure event is you can reach an LEL within seconds, and you may actually see exceed the upper explosive limit within minutes. So just to give you guys some quick references, this is something I borrowed from UL. I've got no problem borrowing videos and information from others, and they're more than willing to share. But you can see this was a 9540A test that was done by UL, and this was the relative compositions that they look at. You can see the venting, that's an off-gas event that you move into. But hydrogen, 32%, hydrocarbons, 10%. And here's a variety of tests that UL has done. Again, NMC, nickel, metal, cadmium, hydro, where we got about 32% hydrogen. These were a number of sources from University of Texas in their research. The blue is in hydrogen, green is hydrocarbons. Now there is some interesting lower density batteries, LFP, that are in here that don't show any hydrogen. I really can't tell you why, but most of them have some component. You can see there's a pretty broad range. Again, LFP, lower density batteries, they don't propagate quite as much, but the hydrogen levels are a little higher. We're looking at 50%. So we had some engineering evaluation where we sat back and said, okay, what does all this stuff mean? So this is one scenario that plays out into possibilities. It has to be evaluated for each individual container, off-gas event, UL 9540A, but here's a process that gets you there. So what we looked at was basically 34% hydrocarbons, 24% hydrogen, but we had a total emission rate, if you look at failure mode, of over 14,000 liters of gas. So we looked at the gas mixture of being the lower flammable limit of 6.2% for the gas mixture. Now it's very complicated, and I will be the first to tell you this is not my forte in life, is to calculate mixed gas levels, but there are people that are very good at it in the world. So that 14,000 liters broke down into emission rates over time, because this is somewhat of a bell curve. As one fails, it propagates to the next, and to the next, and then the first one starts tapering off, and then the other ones have entered the range of providing gases. So overall, we had a bell curve of emission rates for a rack over about 24 minutes. And you guys are welcome to pull these things up and look at it. I'm not going to try and read. There's an awful lot of information on these. So a couple of the other assumptions we put into it was temperature increases approximately 3 minutes between failure modes. We looked at a peak emission rate of around 5,000 liters per minute, or around 177 CFM. So one of the things that I always throw out is what burns doesn't explode. So if this gas is being burned off, obviously you're not going to be in a position that you're going to create an explosive atmosphere. Lost that one. Let me go back. All right, so this is a particular cell module that is being tested. Again, you can see it takes off pretty quickly there. So there is no explosion, but it is a very energetic fire. Imagine if that module was in between a rack and what that would do to the impact on the other modules in failure modes. So this is another test. And the odd thing about these batteries is they don't always perform the same way. Now keep in mind, these failure modes are being pushed hard to failure. This is not what you're probably going to see in a normal environment. But if you look at what's being produced there, there is no venting on here, but there is a chimney in this test facility. So you can see a little bit of the gases going out. But in general, that's producing 30% hydrogen, 10% hydrocarbons. It didn't catch on fire, but it is certainly filling the room. So it's interesting to watch the sequence of events here. And this particular failure mode is slightly different than the last one. Throughout wait a minute, guess what? It did catch on fire. It took about 20, 30 seconds before that actually went into a flaming condition. And if you'll notice, the smoke in the background actually kind of cleans up. So it burns off that mixture, that cocktail that's in that atmosphere. Now, this is even more of a wake-up call. The fact that there's explosions out there are a very real event. I've been involved with some personal testing that after a period of time with suppressed fire, we did see explosions. One of the things that I question about in Arizona is the tests that I've seen that the actual failure mode sped up once it finally blew up. And that didn't happen in Arizona. The rest of the cabinets didn't get impacted to the extent, but I don't really know why. But it's an interesting question. So this was a test that went very bad very quickly, that the gas production levels picked up and they were trying to actually get the venting turned on. And you can see that it blew up in the middle of it. So that's always interesting to watch twice. Fortunately, no one was hurt. There was enough capacity to burn to allow the explosion to go out. One of the areas you guys may have seen is Korea. There was a number of fires that we know about, and I'm sure there was probably some more that we don't. Not every one of them always makes it public, but there was no explosions in Korea. And again, this is my own opinion, but they were very limited in what they had for control suppression. Even if they did, they were probably designed to an electrical fire. So for the most part, things in Korea burned. But keep in mind, and this is really hard to read too, so I apologize, but if you look at pressure waves, you can see that even at a 1 PSI, you're going to knock somebody over, you're going to do a little bit of damage. And we're seeing pressure waves depending upon failure modes. Again, this is relative just to give you guys an idea. We're seeing pressure waves at 1 PSI at 70 to 100 feet from containers. They're looking at 15 PSI within a couple of feet. So there's some pretty significant pressure waves that can be generated from a failure mode. So just some quick back of the napkin calculations. If we took a container, looked at what the free volume was, what's the LEL, how much gas is it produced? A lot of questions here and a lot of assumptions. It would take about 26 cells failure to reach LEL on hydrogen alone, which is about 1 module. So that's enough to put you in an explosive environment in a container. Now, as I said, kind of keep in mind, there's a lot of assumptions done here. There is a method to do this evaluation, but you've got to figure out how are we going to determine what the failure mode. So there's no flame production with these examples. Gases are not being vented. There is some airflow. We are looking at a range of LFLs. So there's a lot of assumptions here. So you really need to make sure there's a complete explosion study to determine the variables listed above, and have you got a reasonable expectation of what failure is. So the off-gassing discharge kind of changes, as we said, a little bit of a bell curve. A single cell is probably fairly linear, but the changes in the modules can change the steepness of that curve. So given reasonable density, energy density, the failure and the gas production is going to be somewhat similar. But the construction of the module may limit that. How long does the event go on? Do you have any exhaust? Obviously Arizona was about 4 hours before there was an explosion. Question that we have out there is, all right, what happens if you've exceeded the upper explosive limit? What happens if you do venting and you bring that back into an explosive range? Are you going to initiate an explosion? Is it better to do that while you have trained personnel on site, or wait it out? I would say that prepare for it and have people on site. So LEL is possible in seconds, UEL in a few minutes. Volume for a container, how much solid space do you have? not only solid space, but what's in the way of your failure modes. Do you have deflagration vents, doors that are going to open? Do you have shrapnel that's going to blow out if it's not a free access area, open access area? But more and more of these things are getting more and more dense, so there's very little free space inside these containers. And one of the questions I have, and this is not my expertise either, but if you put a clean agent that's going to increase the pressure inside the container a little bit, what type of design considerations do you have to take for an off-gassing event so that your air pressures in the containers are dealt with appropriately? This little diagram is just what it takes to move that amount of CFM through a bathroom fan. It will take about 45 minutes to move that amount of air. So thermal runaway critical path. One of the most important things with this is outside of our control, but it is so critical. The BMS, battery management system, should be able to monitor for stray voltages, look for heat conditions. So if a battery is starting to go into a failure mode, that should be the time that it's shut down. So I always say maybe the first 15 failure points are all associated with the BMS. But of course, we don't put fire systems in for things that work right 100% of the time. So this is redundant backup systems to make sure that the BMS doesn't do its job. There is a very short window from off gas to thermal runaway. It could be seconds, it could be minutes, depending upon the failure mode. This 9540A test, where they basically take it and burn a bunch of batteries, they push the batteries hard to failure, and you're not going to normally see that in the industry. So once a cell is engaged in thermal runaway, it cannot be stopped, but hopefully what we can do is put in mitigation measures that slow the propagation, keep it a little bit more under control. A battery in thermal runaway, but not on fire, will generate about half the heat as a flaming condition. The thing that we've seen when they're burning is about 1,000 degrees C. When they're not burning, they still propagate at about 400 degrees C. So sometimes what you're going to see is not an immediate explosion, but you may create circumstances where you have delayed explosion. Make sure you understand that risk when you're putting these systems in. Are there unintended consequences? So sprinkler systems may help stop the spreading, but they traditionally are not very effective at penetrating the cabinet and extinguishing the fires. They're very good at heat transfer. So when you look at a 0.3 density, does that really work? Probably not. FM has done some large-scale testing. But then how do you get in and use water as a viable backup? So how much water is available? What's your physical configuration? 855, NFPA 855 only recognizes sprinkler as a viable option for suppression right now, but there is a TIA going through that's actually going to limit that. Only for small systems are you allowed to use water. Anything above that, you have to do some large-scale testing to figure out whether it's going to work. So I mentioned the 0.3 density. It was interesting from what FM did. Instead of giving you a density, what they did was came back and said, let's provide separation. So instead of being able to put racks right next to each other for certain types of batteries, you need 9 feet separation. Now, that's not really going to happen in the world. Utilities, developers are all trying to pack as many batteries as close as they can inside a container. So that's going to be interesting to see how that plays out. But none of the codes are really set to address this. So defining to 13 or 15 don't really give you real good guidance on lithium ion. So a lot of what we're seeing in the world is put as much water in as fast as you can, kind of fill the container up, almost make it into a swimming pool. And believe it or not, that's one of the options that has been proposed out there. Put water above or below, just fill it up real quick. I think we're going to see some changes in the way batteries are managed because of the 9540A. People are looking at configurations that will help mitigate failure pathways, and I think in the next year or two, we will see some different approaches to how this stuff is worked on. So keep in mind, clean agents are very good at Class C fire, and they would do a very good job on that. So anything inside the cabinet building, non-battery fires, they're going to put that out and they're going to save you batteries. But you need to test for an electrolyte fire through a cup burner test, and I would say most of the manufacturers have done some good history on that to tell you what type of concentrations. But you're looking at almost twice the concentration in agent, suppression, whatever it may be, going from that class C to a class B. And one of the things is how do you release? And we're looking at multiple levels, possibly smoke. Generally, smoke is too late. Heat, BMS, while not listed, is a very good indicator of where there's failure modes happening. I can tell you that you've got some stray voltage, that you've got some heat conditions that may lead you to a fire. So I would never release on that, but it's not a bad indicator for your fire panel to pick it up. I would very strongly at first, mitigation, early detection. Redundant to failure to the BMS, off-gas is a very early warning and can help you. It may not stop it, depending upon what the failure mode is, but it's obviously something that can help mitigate. Explosion can be a greater hazard than the fire, so you may find yourself in a position that venting has to take precedent over and should override suppression. So if you release the system, but you're still seeing high levels of gases, you may have to start venting. So it needs to be monitored as part of your complete system to understand, are my gas levels still rising? And in a small container, it's hard to vent the amount of gas production through failure. Again, look at the 9540A test, and it may tell you how much gas is being produced and the best way to deal with that. Now, this is actually a Korean camera inside another fire. And I have no idea what they're saying, so. So as you can see, really it's a very short period of time from that going into failure mode and off gas to the point that it's in the flame mode within about 20 seconds there. That engulfed a pretty good portion of that container. You can see what it looked like when it was burned. So they burned down to the ground. I've got a question here, Todd. How well sealed are these containers? Do they have special provisions into them to provide a tighter seal? There's a very broad range of quality of containers. Some of them are, Swiss cheese. Some of them are built to some very good standards out there. And depending upon your failure mode, because that's part of it too, is where is it going to blow out if it blows out? Some of them have very weak ceilings and may go out the top. Some of them may lose it through the door handles. So it's kind of hard to define that. It's, again, one of those things that you got to look at and figure out what's the appropriate failure mode. Once you've done an explosion study, they're not particularly cheap, but they can help you define for a site. If you've got 5, 10, 20 containers, then you probably will define what's necessary for protection across the rest of the site. So there's the container at the end of the day. Not much left. I'm okay with the concept of let it burn, because if all else fails, if what's burning does two things for you, which burns doesn't explode, and it removes stranded energy. So if a battery's burned up, there's no energy left in it. But keep in mind, maybe all the batteries are burned, maybe they haven't. So you can't ever assume that all the energy is removed. But if something's burned to the ground, you probably have removed a good portion of the stored energy, that stranded energy. But it's really hard. I think it's taken them 6 to 8 months to remove all the batteries from that facility, because they have no idea what the energy is, what the stored energy still is residual. So part of what we look at is for first responders, safety is impact on risk, hazard mitigation, failure means analysis. Is your location remote? There's a lot of exceptions for putting something 100 feet away. And again, if it's an asset that they can afford to lose, sit on the outside watch. Do not enter. Do not jeopardize life and safety. A life is not worth an asset. An asset is not worth a life. Reverse that. So make sure you've got an emergency response plan in place. So if somebody's coming to that site and we've got systems out there, what are they doing to make sure that everybody else is kept safe? Look at a phased approach. Make sure you've got gas and off-gas detection, multiple levels of suppression, initial system, and ultimately backup system. Part of what you're dealing with as well is what does the market offer to you? You got to deal with standard gas detection. One of the problems we run into with monitoring hydrogen is if you've suppressed the catalytic bead's ability to monitor hydrogen, are you going to get true readings? So you might have to look at a reference gas because those hydrogen, as far as I know, can only pick up on a I'm sorry, I'm saying the question come in, but hydrogen can only be picked up on a catalytic bead or type sensor. It can't be picked up on an IR. So it has the potential to get fouled. Another question, is there a benefit to shutting off the charging circuit as soon as detection occurred? Absolutely. If you can take it off load from that off gas, which is charge or discharge, you run a very good possibility of stopping it from going into thermal runaway. But that time frame can be short. As I said, it could be seconds, it could be minutes. Depending upon the failure mode, you may have as many as 15 minutes, but you absolutely want to take it off charging as quickly as you can. But keep in mind, taking it off charging does not eliminate the charge that's already in the battery. So there's a very difficult to take it and discharge that energy, because effectively, if you're discharging that energy, you're back into a usage mode that will increase the short circuit again and push it into thermal runaway. That's one of the challenges that the world has got out there, is how can they discharge that energy quickly without making the problem worse. So there's available data, where and how is it applied? I mean, one of the things is how are they building the modules? UL defines cell as a battery, module as a drawer, a unit as being a rack, and then installation being everything above that, whether it's a container or a building. So understand how it's put together, what are the physical constraints, what are the physical properties. Again, unintended consequences, what happens if it's too rich to burn. Then shutdowns, how do we turn off power? Because ultimately, code doesn't really address this for an event that could go on for 4 hours, 5 hours, 2 days, because they can reignite. So what do we do for battery backup, not only on our systems, but on the BMS systems as well? It's kind of ironic having battery backup on a battery system, but ultimately you've got to figure that 5-minute alarm is not going to give you enough safety if we've got a high gas level event. So we've got to be looking at what options may come up into the world on making sure that first responders are safe and has information. We push very hard for remote technologies. Put something at the fence line. Let the first responders have access to data. Lights on the outside are also very critical. I got 2 more questions here. We'll see what it says. Actually, I got about 3. For sites that have multiple containers, are there any concerns for container-to-container propagation? Absolutely. One of the things we look at in the code and heat transfer is about 10 feet between containers. So there needs to be separation. I hate to say it, but one of the best suppressions, one of the best controls of these fires is separation. Keep things further apart as much as you can so that if one goes, it doesn't carry on to the next one. So separation is a great equalizer in these systems. Have radiant energy sensing detectors been evaluated in order to initiate activation of the fire suppression system? It is happening. There are some tests going on. There's a number of sensors that have been deployed for some of the big testing agencies to see if we can get data. It is still very sketchy, but I think that's a very good option when we come to detections. If you can read down the hot aisles, I think that's a very good option. Next question, how would you approach putting this type of system in a high-rise? Very carefully. I could say next question, please. But when you start looking at mixed use occupancy, there's a lot of other safety things that go into it. I wouldn't put something in there without having 3 or 4 different levels, including early detection, deflagration, initial suppression, high level detection, and then water as a backup, and then separation as much as you can as well. So high rise is a very scary proposition at this point. All right, let's go on next. Understanding the process to failure is critical. Make sure you employ somebody that can give you what information you need, both in the design, from a management standpoint, and from a site standpoint. Modeling tools can only get you so far. You've got to work with what's commercially available in the industry, and how quickly or what are your assumptions? So your failure rates, where it fails. You know, did a battery fail in the middle of a rack in the back corner? Was it up at the top? Is it at the bottom? Can you get partial deflagration? There's a lot of different questions that go in there. There are not any silver bullets yet. You can only burn so many batteries. They get a little expensive. People get a little cost conscious when they have to burn a lot of batteries. So what I'm looking at on NFPA 855 is it's still a little bit behind. There's over 15 task groups going into 855 to try to catch up with some of the things we've learned in the last year, sprinklers just being one of the many. How do we deal with gas detection? How do we deal with explosion? How do we deal with exemptions? So this code is currently published. It is on the street. There was over 1,200 public inputs that went into this. It was 12 days of review. Over 12 NITMANs were filed, number of TIAs. The Standard Council chose to publish without a scope because it was challenged. It was wanted at a membership level, but it lost at the committee level. So it's interesting, and I really don't know how that's going to play out from an AHA standpoint, is what do you do with a committee that has no scope? So here's what was proposed. Went through several iterations. Here's what the utility members proposed. They wanted to be exempt. And ultimately, as they said, this is what they got. What do you do with that? So my recommendations to you is keep aware of the code cycle, engage. If you guys see things are out there, the code cycle is currently open. 6:30 is for public input. Submit changes. Get as much information as you can. There is a little bit of fear for first responders out there. They're not really quite sure what to do with it. But bring them in early. Have conversations with them. Let them understand what things they're dealing with and what possibly can happen and how to approach it appropriately. I'm seeing a lot of training in the industries from people employing these energy storage systems right now. All right, I got another question over here. Let's see what we got. Would a water mist system perform better than a clean agent system? I would say that water mist right now is unfortunately one of those things that I'm looking at as a brown paper bag. There is a DNVGL report out there in the marketplace, and if you want to ask some questions, Jonathan is a very good resource on that. He has been involved with a lot of different testing. I would say it looks very promising. It does a couple of things. It actually scrubs the air. It brings some of the particulates and contaminants out. Small water droplets do a very good job of that heat transfer management. And then there's the suppression capability of removing the fire. So it flows like a gas. I think that's a great option and a great opportunity. The data is still somewhat limited. You know, it's coming, and hopefully we'll see more of that as the world goes on here. But I think that's a very good option. So understand the risk. Apply appropriately to the location. This is not an electrical hazard. Believe very much in a phased approach, starting with the BMS. Make sure that the product is able to monitor and look for failure modes on its own. Where the technology is applied matters. Are we putting it in a building level, container level? Are we applying it directly to the modules themselves? And we're seeing that approach happen through a lot of the UL 9540A. That's what gives me promise that a year from now, we'll see a different application that will limit propagation. And when propagation is limited to maybe only a module, that means gas production is a lot less. And we'll probably see it shift back to an electrical type hazard that we can deal with without having to deal with all these other implications. It's not here yet, but it's heading that way. So do not endanger life and public safety. Keep people out. Don't let them go in. But balance the risk versus technology available. You know, a location that's set up next to a store is going to be a lot higher risk or a high rise than something out in the middle of a cornfield in North Carolina. Arizona has created a major shift in the industry. We are seeing a lot of people step back and evaluate what they're doing. That's not everybody. So there are still thinking people, how quickly can I employ this at the minimum cost? And that risk exists. Be careful with those because anybody can be picked up as providing a piece of equipment, and make sure the rest of the equipment is in place and working properly so that you don't get caught when somebody else fails to do their job. So there are practices to help us work through this, but it is based on assumptions on assumptions on assumptions. Ask for the burn test. Have they done the data? Where's the 9548 data that helps define the hazard? Have they done an HMA? If they're asking you guys to provide a system, show me where you've done the hazard mitigation analysis that this is an acceptable way to mitigate your failures. Do not provide one piece of equipment and assume everybody else is doing their part. So what are the solutions? Kind of mentioned this earlier, multiple levels. Protect the module. Look for gas detection at the module level. Look for gas detection at an installation level. Then some type of installation suppression at a building level, container level, whatever that may be. Then if it's just pumping water in, making a dry hose standpipe and letting them hook up and fill the thing up with as quickly as you possibly can. When all else fails, if you can do it, let it burn. It's not really a great statement for somebody trying to sell equipment, but ultimately we want what works for our client. So I'm not opposed to that. There's still some other products we can apply. So I made a comment earlier, what burns doesn't leave stranded energy, but keep in mind that that's complete combustion. So if you don't have a complete combustion, then yes, you have the potential to have damaged batteries. UL will not run fire tests on batteries on Thursday or Friday because they've got to sit around for 2 or 3 days to make sure that they do not reignite. And that is a very real possibility. They've doused them with water. They put heat sensors on them. Everything is cool, everything is clean, and the next day they catch fire again. It's that battery churning that's got a very small short circuit that's been damaged that overnight proceeds to a big damage. So ask, what is your hazard mitigation analysis? What is your first responder plan? Do you have a first responder station that allows them to not go in? Failure modes and effects analysis, an explosion study. Really should be looking at that and asking that, did they provide that? Are they providing deflagration calculations? Signage, more so, stay out. Special matter expert, has somebody been involved to help them understand it, and then training at the end of the day. So there's unintended consequences. Events are rare, but they can be catastrophic. What is your design criteria, expectation, extinguishment, suppression, control? They all have a slightly different approach in what you're going to do with your equipment. Fire and explosion, make sure you are covered. You need to make sure that both of them are taken into account. And if the 9548 says there's no gas production, then that's what we need to engineer into our calculations, that explosion is being taken care of. One technology is probably not going to be adequate, but if we layer on top of layer, it helps mitigate the failure pathways. And we still have a lot to learn. I encourage everybody to share best practices. If you know something, let us know. We are trying to actually work a suppression guide for the industry. It has been presented to the Standard Council that allows Guidance on lithium ion. I think it's important that we put that out there. Hopefully it'll come out as maybe like an 855A. It'll still be a little bit down the road, but we're trying to write that. And I know some of you guys are probably helping and supporting, but if you feel like there's a technology or an advantage, we're going to try to push that. It is being supported by the NFA 855 committee, and hopefully it'll be approved in April. Well, they're going to review it in April, hopefully in the August meeting, depending upon how meetings go over the next couple of months. We may see that guide come under construction. So one of the things I always say is failure to plan. I have no idea where this job site is, but how do you put a pipe through the middle of a door? Another question that came up, do you think the UL testing will identify the existence of an explosion hazard? Yes, they are working on that right now. They are trying to incorporate that into their test plan. While they've collected the gas, they haven't done a lot to figure out what that potential hazard means. And there was an interesting conversation yesterday on EPRI. Safety Council is trying to write some standards as well. FM got involved in the conversation. And what they want to do is show, okay, a module didn't propagate, didn't catch fire, but it produced gas. So do you add an external ignition source to that in order to light that, with the assumption that maybe the batteries may not do it, but if there was a failure mode in the power supply or some other electrical that could not ignite that. So I think you'll see that coming, that explosion hazard will be much more of an evaluation, both by FM and UL. So guys, that is the end of the presentation. I want to thank everybody again for being here. If there are any other questions, please put those through. Todd, you can
Paul, thank you. Thank you very much for that presentation. As I mentioned in the beginning, it's an extremely hot topic. You provided some great information, some great insight. You did a great job answering the questions along the way, and I know there's a couple more coming in here as I'm speaking, so we're going to go ahead and answer a few of those as well. I'm going to go back, Paul. In the beginning, there were two other quick questions, I think, in the earlier portion. One was, that I missed. Can you discuss nitrogen inerting options for these boxes?
I would tell you right now that we don't have a lot of good information on inerting. I haven't seen it. Again, I'm always welcome to somebody providing anything. Again, you kind of get into a suppressed atmosphere, and the batteries don't need an atmosphere to propagate, and that's a concern with any type of thing that extinguishes the flame. And again, some batteries reflect differently on how they fail and the amount of gas, so you need that data. And if you want to incorporate nitrogen into their testing, that is always an option. But part of what we're going to end up having to say with this suppression guide is there's going to be some technologies that we're just going to have to say right now, there's not been any testing, so we can't advise you one way or another. It is not part of 855, so therefore it technically is not allowed. However, keep in mind, 855 has not been really adopted in the marketplace. It is out, but a lot of the other states are dealing with IFC and 608, New York, Arizona, in some modified standard, California. All of those are kind of working towards their own adoption, so I don't know exactly when 855 will be adopted.
Great, excellent. Another question from earlier, what technology do you recommend for temperature monitoring?
Well, there's a couple of things that happen inside the BMS. Most of them are trying to monitor temperature, and it's not so much from a fire. Most of these batteries have warranties that they have to be kept within a certain range of temperature. So they're kept temperature inside the enclosure is largely done by the BMS to make sure we're within that control. When we look at other temperature type detection, it is a very slow response, as you guys know. So we add it as a layer if there may be some reason that something else failed, protect the wire, fin wall, whatever you want to add in there. But it is kind of a last resort. The one other temperature, as kind of mentioned earlier, was that thermal imaging camera. Those seem to be very good, but it takes a very good line of sight. So if we can get a good image down a hot aisle, so to speak, you may be able to see a 10-degree temperature swing from failure mode to 80 degrees, 100 degrees, depending upon where you are. And even external to a balance of plant type situation where you've got 20, 30, 50 containers, you might look at an external camera to look at the field of view to see if any of the containers are increasing in heat. Now, at that point, you're probably already lost that container, but there might be some ways to make sure that it doesn't propagate between other containers.
Right. Okay. And like we typically see on these webinars, now we're getting a whole flood of questions coming in. So we're going to stay on and go through a few of these questions and try to get to everyone. The next question is, and this is a little lengthy question here, in the co-location data center space, UPS room containers are becoming important to supply chain management and fast deployment. The maximum size in NFPA 855 are very prohibitive to this approach. Do you know of any mitigation being considered to the maximum dimensions direction for containers not dedicated to energy storage?
I'm seeing that market change. I'm not sure I have a real good answer for this, but I know that what's happening is the backup UPS market is starting to look at lithium ions so that they can use it not only as backup, but they can use it as storage and to manage the building. I can tell you that I've talked to some people that have done that. They put it in their basement. It blew up. It was one of the major companies in this world, and they lost their whole campus for months at a time. So it's again, probably if I had to say you were putting it in there, I tell if you want to design, hire me as a consultant about putting that in your building. My answer is don't. That'll be $10,000. I would say that that's something that needs to be moved outside the building as opposed to internal. But I know it's coming, and I don't see a whole lot of good options for controlling that failure in a very small system. That 50 kilowatt hours is prohibitive, but hopefully that'll keep some control on some of these smaller systems that are coming in. And it is being addressed in the world and the marketplace, but it is going to be more prevalent.
Okay, great. Thank you. Is there an average temperature that you are seeing that the electric light flashes, or a temperature that causes the electrolyte to pop the safety cap or vent or and vent?
Yeah, we start getting into, I think it was on, I'm trying to think it was on that UL slide. Are you guys still looking at my screen? I can probably run back.
Yep, we can still see it.
There is some data in that, and generally at 130 degrees C, they fail completely. But that range that you start getting into, I want to say 70 and 80 degrees C, is where you start seeing some failure modes. Here we go. This particular one was 98. This is the UL testing that they see. 98C is started venting, and 185 degrees it went off the charts. So that's a relative range. I've seen them again more 130C, somewhere around in that they can fail. Depends upon the battery, and that data, if they're burning them, should tell you where they failed.
Okay. Should container design include the thermal runaway analysis?
And I would, yes, I would say look at it as an explosion analysis. If you've got the data from your 9540A testing, in general, what that says, if I summarize it, take a cell, burn it, see what happens. Take a module, burn it, see what happens. Take a rack, burn it, see what happens. Take an installation, burn it, see what happens. But it gets very expensive when you start burning whole installations. You start spending, $10 million on a cabinet. They don't like burning those very often. The cell's not that bad. So if they can show propagation, limited propagation beyond a module, then they really shouldn't be doing further testing beyond. But it's not a pass-fail. It's here's what happens. So there is no end result that says, yes, you're good. No, you're not. So thermal runaway, you're going to get thermal runaway in a battery. It's going to happen. There's just to an extent. Does it ignite? Does it propagate? Because what they do is they purposely drive it into the thermal runaway. But beyond that, do the explosion study. Understand what the container design is and what you can vent reasonably based on the failure modes to get that gases out. And it may be a deflagration vent if it's a very small container.
Right. Okay. Would CO2 be an option for suppression?
I find that an interesting option. There hasn't been any testing on it yet. What makes it interesting is that you could continue to inert that atmosphere for hours at a time, that you could provide some, a larger tank. But does it become cost prohibitive to put a 10-ton tank out on a site to protect a 30-foot container? It's not going to provide you any cooling. It will suppress it. The batteries probably will continue to propagate depending upon their configuration. So I don't see it yet, and there really hasn't been any testing.
Okay. We do still have a few more questions coming in here. I know it's just at 1 o'clock. We appreciate anybody that does have to drop off, but if you're interested in hanging out with us for a little bit more time and listening to the additional questions, please do so. Paul, the next one is, do you think NFPA 855, the valid guidance to follow design as it is behind now? What do you think is the best off-gas detection at the unit and module level? So 2 questions there. Sorry.
This is my personal opinion. I think the 855 committee did a good job with what they had to work with. What we're understanding in education in the last year is there's a lot of holes. So there's not a real good design guidance in there right now, especially when it comes to venting, gas detection, suppression. I think there's very limited information. What was there got pushed to the annex. We're hoping to draw it back out. So it's not really a great guide for that. Some of the 608 codes may be a little bit better. When I look at gas detection, there is only really one product on the market, that is Lion Tamer, to pick up that off-gas detection. But it is gas detection. It's more of an art than it is a science. So depending upon your failure modes, it should pick it up, but it may not, just because the airflows may be in the wrong place and the timing on it. So that is at an event, at a module level event. But if we look at a unit level event, there's a lot of gas detections on the market out there, and I won't pick one in particular. I have a tendency to look at both hydrogen and CO, because if your hydrogen is not reading the way it should, CO can work as a precursor gas. Rising levels of CO and or CO2 are going to indicate more likely you got some other things being released at the same time. Right. So those are good options, but you really need to look at a building or unit level event beyond just an off-gas. Off-gas is early warning detection.
Gotcha. And I think back to the NFPA question, I mean, those are always evolving documents, and every day we learn something new that, applies to these different documents, regardless of what NFPA standard. And that's why we have the committees doing the hard work that they do.
Yep.
So the next question is, will codes classify hazard areas as Class 1, Division 1, or Division 2? That's a good question.
I love this question, because right now it has not been addressed, and it is coming, and it is going to cause an upheaval in the marketplace right there, because ideally the way the code was written right now is it evaluated gas under normal conditions, meaning sealed lead acid batteries. So the committee asked me, they looked at me and said, well, can we put sealed lead acid batteries in a confined space or a hazardous space? And I looked at them, and I thought that question's in reverse by the fact that putting a lead acid battery in there, you make it classified. So given lithium ion has the ability under abnormal conditions to produce gas, that's the definition of a Class 1 Div 2. It's not in there now. People are not building it, but it is a question that will take the market over at some point in time. I don't know when, but it is a very good question.
Okay, excellent. Referring to one of your slides here, you had shown the large pouch cells, and then in 18,750 cell are both used in these large systems or only pouch?
I would say we see more pouch cells than anything else, but some of the other type products are out there in the marketplace. I don't really know. Probably the 8650. The other cells you might see in the smaller applications, building type applications, wall type applications. But in your Ryobi has got the smaller cells versus the pouch. But big systems are more likely the pouch. Yeah, the 18650. Sorry, not as much in large, mostly a pouch. But the LFP is an option, and that's kind of a different configuration as well. That pouch is more of an NMC. There's a lot of something will change in the next couple of years, next 5 years, 10 years. I don't know when. But there will be a disruptive technology again that will change our energy storage. And what will the unintended consequences be?
Right. Okay.
I think, Todd, there was a question before that.
Okay.
Hydrogen sensor.
Yep. Yeah. What are you placing the hydrogen sensors within the ES? Where are you placing the hydrogen sensors within the ESS?
Trying to get them into the appropriate airflow. Depends upon, most of these modules have airflow from the front or the back or the back to the front, and they create kind of a hot aisle. So ideally, we'd want to locate that into a space, or even with air conditioning, wherever we're pulling HVAC, someplace that would allow us to pick that up through that position. So you got to do a little bit of modeling and understanding your airflow to figure out where that hydrogen sensor is going to go.
Okay. And then the last one we have right here now is, would high expansion foam systems work well extinguishing the fire and cooling the system?
Again, no testing has been done on it. I think there's some people out there that are using some of the products that are not really the high expansion, but they're additives. That helps to get into the cabinet if you can get the water down to that level. But high expansion foam, in my mind, doesn't do a good job of absorbing heat. It will probably extinguish the flame, but it's not going to remove the heat. And ultimately, I'm hoping one of these solutions has the ability to deal with that heat transfer issue as well. So we can eliminate or remove some of that heat. The potential for other sales to fail will go down. But I don't think a high expansion foam at the moment, until we get some testing, is not on the top of the list of what I've been looking at.
Okay. Okay, and I'll also add to that as well that, it is important for all of our listeners to note that, all the information that's gathered and that Paul's presented, it's based on what's out there. There's a lot of questions on what type of system, how, why, when type scenario, and if those testings haven't been completed by an association or an individual, it's really hard to answer that. And yep. Saying what you said in the past, there really is no silver bullet and there is no pass or fail. I like both of those comments. Those are my takeaways. and that's something that we all have to understand. It's a hot topic. We're learning every day. More to come, I guess, is the point, and stay tuned. So with that, I really, again, Paul, thank you so much. I appreciate everybody, all the listeners that are on today. There were a few questions, Paul, about the availability of the presentation. I know for all the listeners, you can download the recording of this webinar in the future. You can certainly reach out to Paul if you have any additional questions specific to his presentation or anything along that line. And I'll let him, if he feels it's available to the masses, that's something that he can discuss with you. But the recording of this webinar is going to be available on the FSSA website. I want to remind everybody again on the opportunities for sponsorships. If you're interested in making sponsorships on the webinar sponsor or the weekly eBlast sponsorships, reach out to Becca at fssa.net. And again, Paul, thank you so much. And I'm going to pass it back here to Becca. Becca?
All right. Thank you, Todd, and thank you, Paul, so much. Thank you to everyone who joined us this afternoon for FSSA's webinar on protection of energy storage systems. As Todd stated, the presentation was recorded and will be available on the FSSA website in the next week. We look forward to having you with us on our next webinar. Thank you.